All right, so we're going to be doing nonlinear equations. I'm going to skip, I think you know quadratic equations. Cubic equations, they actually do the exact cubic formula. I'm not going to do that. So you have these bisection method, Newton-Raphson method, secant method, false position method. These are all numerical methods for finding roots of equations. Now, you know quadratic equation is to find roots, right? Mm-hmm. And these are all numerical methods. Okay. Newton-Raphson, secant, false position are all very similar. You may have seen the Newton method before. Newton method involves derivatives, secant method does not, and false position is similar to secant. Right? So these methods are all quite related. Bisection has a very simple idea. Bisection, you just keep. Well, let's go there. By the way, let me see if I can get some feedback. How are you doing with this material? Is it clear? Can you understand his? Yeah, sure. Can you understand his accent? Have you watched the videos?
Really not bad.
Yeah.
Dr. Grant, I had Dr. Abani for 3 classes. I think I'm good.
Okay.
I don't know about you.
Yeah. Okay.
I've read through a couple of transcripts.
Uh-huh.
Noticed that he basically reads off exactly what's in the book, which is what's on the presentation.
Okay,
So
all right.
just
Yeah.
read through that.
So whatever you want to do. I watch videos and I speed it up twice. So.
Yeah, that helps.
Because, but anyway, I think he did a very, very good job of organizing this material. That's because he's an engineer and not a mathematician, so he knows how to do things right. So, anyway, bisection is a very simple idea, and I'll just sketch it briefly. Again, he could probably explain it better than me, but I'll just say how it works. And so I'll say it very quickly, and then you can reinforce by watching him. If you have an interval, so I think that's what I'll do is I'll sketch the pictures for all these methods. These methods are all very pictorial, right? So if I have an interval from A to B, and if there's a root here somewhere, let's suppose that I've chosen A and B so that there's only one root in there. And so that takes some extra knowledge. You may not know that immediately. But let's say there's just one root. Okay. Now notice that here you're above and here you're below. Okay. Actually, let me do it differently. Because if I do it in the middle, let's put the root over here somewhere. Let's put it closer to there. Okay. So here you're above, and this is the x-axis, right? And here's the y-axis here. Here you're above and here you're below. So there must be a root in between that follows from the intermediate value theorem from calculus. All right. So let's do this. So this is I'll label this as plus and I'll label this as minus. Okay. So I have no idea where the root is, so let's look in the middle. I'll look in the middle. All right? Now this one is up, right? So this is another plus. So now look, this one's plus, this one's minus. There has to be a root somewhere in there, right? Okay? So let's look in the middle. Okay? So if I look in the middle, now this one's plus. So this plus means I look over this way, right? This one's plus, this one's minus. What does that tell me? It still has to be on this side, right? It has to be somewhere over here. All right, I do it again. Okay. Now, this one's minus. What does that tell me? You have to go back, right? Okay. Now, here's a plus here. Okay. All right, so you keep dividing, and you get closer and closer. Okay, pretty cool method, huh? Very easy to...
It kind of reminds me of the squeeze theorem.
Yes. Okay. All right, so you can do this numerically, and it's very dependable, as long as you chose your initial interval the right way. Things can go wrong. You could have 3 or 4 roots there, but even if you had 3 or 4, it would get to one of them somehow. You could ask, why choose in the middle? Why not choose somewhere else? Well, the middle makes sense But it turns out that the middle is not the best way to do it. But anyway, he taught middle. There's something called golden mean method, which is better. But anyway, he taught bisection, so we'll do bisection. The idea is the same. All right, so that's bisection. Okay, pretty easy.
So is that the squeeze theorem that you learn in, I think, Cal 1?
Well, no, it's not quite the same, I don't think, because here you're just using intermediate value theorem. So I think that bears some resemblance, but but that's pretty much what it is. Okay, so Newton method. Okay, so in this case, let me draw this, and let's suppose there's a root here. I've drawn this picture before, but it's not always so easy. Let's do that. All right. All right. So in this case, I don't need an interval. I just need a starting point. So I'm going to choose a starting point somewhere near where there's a root. Right? I want to get up here. Right? Okay. So I'm going to choose a starting point here. So this is my root. I'll call this x0, and I'll just call this a. That's my initial guess.
This is one that's similar to like Euler, right? Where you kind of guess and you get closer to it.
Well, you'll see. Yeah, I think it's something like that. Yeah. All right. So here I take my a, and I take, right. Actually, I think I'm too close to the previous one, so I'm going to have to. Here, let me just. I'm going to move my a a little closer. All right, let me move my a a little closer. And actually, let me move the whole thing down so I don't bump into the other one. That's the nice thing about this thing here. I take my whole axes and move them down. Like this. Okay, let me move them down a little bit. Okay. All right, so here we go. And here's my x0. This is my root. Sorry. And I'll call it x0. And here's my initial guess. I'll call a. All right? So if that's a, then this up here is f of a. Right? So I want to get to my root. Now suppose I know the slope of this line. Suppose I know the slope. All right, it's lousy slope, but I mean, I'm a mathematician, so you get what you pay for. All right, so if I know the slope, where should I guess the root is?
Where the slope intersects the...
Yeah, take this line down. I'm sorry, that's just too bad. It won't pass. Okay, all right, so let's do it this way. I should just do this. I have to learn how to let the computer think for me. I can do a straight line like that. Okay, here we go. There we go. Now I can do a very nice tangent. Whoops, but it doesn't. All right. Okay, there we go. Okay. All right. Okay. Okay. So this is the tangent line, right? At the point A and f of a. All right. Now, this point here is pretty close to the root. The only reason why it's not at the root is because it curved out. If this function were straighter, it'd be a much better approximation. But because it's curving, it's off a little bit. Right? So, this point is a better approximation. So this is... So the question is, what are the coordinates of this point? Okay, this tangent line has the slope of tangent line is equal to f prime, right? So what's the coordinates of this point in terms of f prime, a, and f of a? Well, you can read about it, all right? But I'll just tell you just use triangles. This is f of a. This is, I'll call this z because that's what you want to find. And you know what the slope is, right? So you just diddle around with your triangle and you can figure out what z is. And this point is a minus z, right? And you'll find the formula in. So I just want to give you the idea. You can read about the exact details. Now, I think it's pretty clear. And then what do you do with this one? You do the same thing.
Just go back up.
You go back up and you just keep hopping. You just keep hopping. You go up, and then tangent, go up, and then tangent, like this. Now, it doesn't always look this way. Sometimes it crosses over to the other side. Sometimes it does weird stuff. But as long as you're close enough at the beginning, you'll get there. And he'll probably tell you about the advantages and disadvantages. I talked about big O, right? So there's a big O. The thing about bisection is that although it's dependable, and you always have the error by 2 each time, that's relatively slow. Here you can cut the error basically by a factor of, well, it's like delta x squared, something like that. So you do pretty good. And here also, it turns out that the error depends on the second derivative of the function. If the second derivative is small, then the error is going to be small. And you can see that because the second derivative is how much it curves. If it doesn't curve, then it's going to be very accurate. All right. So that is Newton. All right, so let's do secant. All right, so that's 2 down, 2 to go. Secant. Now, the disadvantage of Newton is that you need to know the derivative. And this one, you don't have the derivative. You don't need the derivative. Okay. All right. So in this case, let's see what we can do. Now, secant, if you remember what secant is, secant means you join 2 points on the curve. Right? So let me draw another curve here. So in this case, I want 2 values, A and B. Okay? All right, now, you remember when I used Newton, I took the tangent line. But I don't have the derivative, so I can't do that. So I'll do the next best thing and take the secant line, which is this. Actually, I wanted to make it a different color, so I thought it was a different color. Let me make it a different color. Make it red. I'm going to take the secant line. And where is it? Right? Beautiful. So this is the secant line. Okay. So my next approximate root is going to be here, right? So this is the new approximation. Okay. Okay, once I found this, how do I get the next approximation?
Well, you take the point B and then find the slope between that and the point.
So let's call this C. Right? So I can't use the derivative, but I can evaluate the function. Right? This is f of c. All right, now the question is, which secant line do I take? Do I take this one or do I take this one?
C to B?
Well, because you can see that, but yeah, I guess it does make sense that this one's positive, this one's negative, one's positive. You might as well do it that way. It turns out that you could do either one. But let's do the one with the sign switch. That's probably good. So let's do another one. Okay. So we've got whoops. So you do this, right? And then you get point D, and then you just go on from there.
All right, if you did A to C,
Yeah.
you have
Well,
no...
you'd end up here.
Oh, you just keep drawing it?
Yeah.
Okay.
Yeah.
I didn't think about that.
Yeah. Because it's the line, as long as the slope isn't 0, you're going to hit the axis somewhere. But I think it is better. I don't know if he chooses the points to change signs or not. I don't know.
I would think that would be the logical thing.
Yeah, I think so. Now, there's one more called false position, and it's something like secant, but I don't remember what it is, so let's just take a quick look and see what it is. I mean, false position sounds like it's bad, but let's see what it says here. And I think there's probably a picture here too. All right, this looks a lot like secant. All right, so let's see. Actually, to me, this looks like secant. All right, so let's see. Here he says to choose X. In fact, I don't really see any difference between this and secant. Maybe I have secant wrong. Because this looks like just like what I did. If you work out the formula, that's what it's going to be. So let's see what secant is. I think the only difference between secant and false position is for secant you always take the last, you always use the last two to get the next one, and you don't worry about the signs. So I think that what I just showed you was false position. Let's look at secant and see what it is. Secant and false position are extremely similar.
Well, it looks like the false position had the absolute value, secant in it.
Yeah, I think that secant does not worry about the. It just takes the last two. So that's the Newton method. You see, the Newton method requires a derivative. Yeah, so that's what secant does. Secant always takes the previous two and uses the next one. So it doesn't look at the signs. Okay. So I can say that this is basically secant and false position. They're about the same thing. And so I can say the difference is the secant takes the last two. Whoops, I'll just say secant, you just can write this with words. Whoops. Okay, the secant uses the ith and I plus 1th approximations to find the I plus 2th approximation. And then false position always uses uses approximations that have different signs of f of x. But they both use a secant line. They both use secant lines, but the 2 points they choose on the curve may be different. So if that's not completely clear, you can read the details. All right. So I think the idea is quite easy, and then you'll have a chance to work through the exercises to get a chance to do the actual calculations. So this is for this coming week, and I'm also going to give you a couple of exercises on campus about what we talked about today, mostly having to do with differentiation of continuous functions and computing those error terms. All right. So I think that's it. So today is a fun week. For you guys who don't like coding, today is a fun week. It's fun for everybody but Luis. All right, so I guess I better stop the recording. If I am recording, I thought I was recording.
Alright.
All right, so we're good. Oh, I am recording. I'm recording this as I talk.